A man pulls a large block of mass M over level ground by a rope with a force F, an angle theta above the horizontal, as shown in the figure. And the coefficients of friction are given as mu k and mu s. So first thing what we're going to do in part A is draw the free body diagram. So we have gravitational force going straight down. It's on a flat level surface, so the normal force is going straight up. The man is pulling it upward at an angle, so we have the Ft, or we can just call it F, because that's what it says in the problem, going up that way, and then the frictional force is parallel to the ground in the opposite direction of the motion. So part B, derive an inequality statement for F if the man pulls with enough force to start the block moving. And then express your answer in terms of all the things that have been given so far, as well as any other fundamental constants. So the first thing is we want to take this free body diagram and redraw it broken into components. So, without rotating the axes, since three of these forces, the upward force, the downward force, and the frictional force to the left, are already lined up with the axes, we'd only have to break this F, or Ft, into components. And the angle is right here. That's the angle between F and the horizontal axis. So when I redraw this, it will look like Fg going down, Fn going up, Ff going to the left, and then the F has an upward component and a rightward component. The rightward component is F cosine theta, because that's the one closest to the angle, and the upward component is F sine theta. So that's the new free body diagram, and we want to now just try and come up with the inequality statement to start the block moving. So the block is going to be moving in the horizontal direction, so the inequality statement would basically come down to, as long as the force on this side is greater than or equal to the force on this side, the static frictional force, as long as this pulling force is greater than the static frictional force, or equal to it, the block will start moving. So the inequality statement we can write will be F cosine of theta has to be greater than or equal to F, the static force of friction. But the answer has to be expressed in terms of m, theta, mu k, mu s, and any constants. So right now, we cannot have this in the equation. We'll have to replace that. So we'll write this as F cosine of theta is greater than or equal to mu s Fn. We're trying to overcome static friction. And now we don't know what this Fn is, so we're going to have to figure that out. Now remember, some problems the Fn is equal to the Fg, and in some problems it's not. See what you can figure it out in this case. Is the Fn equal to the Fg? And the answer is no, because if you look at this diagram, the forces in the vertical direction are balanced. The horizontal direction is going to become unbalanced once he starts pulling it, but the vertical direction, the block is not moving vertically, so the upward forces have to add up to equal the downward forces. So if I write that out, it will be right over here. The net force in the y direction is equal to 0. Newton's first law in the y direction, since the block is not moving vertically. And we're going to set up equals down. So that is F n plus F sine of theta, those are the two upward forces, equals Fg, the downward force. And rather than write the Fg, I can just go ahead and, let me just go ahead and put in the formula for it already. That is m times g. And then in the first formula, we have this Fn that we didn't know, but I can rewrite this other formula to get Fn by itself. So that will become, I'm just going to subtract F sine theta from both sides. So Fn is equal to mg minus F sine of theta, and that formula we can plug in right there. So it now becomes f cosine of theta is greater than or equal to mu s times, now I'm going to put all this in parentheses, mg minus f sine of theta. And now if you look at this whole formula so far, we're trying to come up with an inequality for f, so we've got the f in there, and it has to be in terms of m and theta and mu k and mu s. So everything in here is now valid. It's all things that we can have, and g is the constant, so that's okay. There's nothing we don't know, but the issue is that we now have this f, his pulling force, in two separate places. We have it over here and over here, and we're just going to want to get one single f. So we're going to just do some math manipulation and try to get the f terms over on one side together. So the first thing we want to do is distribute. So I'm going to have f cosine of theta is greater than or equal to mu s mg minus mu s f sine of theta. And then let's take this term, this whole term right here, and move it over to this side of the equation. So, and I'll move it down a little bit so we have a bit more room to see things. So we're now going to have f cosine of theta plus, since I'm bringing this term over to this side and it's negative over here, so it'll be plus over here, plus mu s f sine of theta is greater than or equal to mu s mg. That was just the only term left on this side. And now we can factor out that f to get f times, in parentheses, cosine of theta plus mu s sine of theta has to be greater than or equal to mu s mg. And then the last step is just get the f by itself. So f should be greater than or equal to mu s mg divided by cosine theta plus mu s sine of theta. And that is the whole inequality. And I realize I probably should have given you a bit more space to work that problem. So now, while the block is in motion, the man suddenly increases his pulling force on the rope. So he is increasing this F, or if you want to look at it on this diagram, that means that both this part, the horizontal component, and this part, the vertical component, will increase. And the question, part C, is does the normal force exerted on the block increase, decrease, or remain the same? Well, when he increases his pulling force, he doesn't actually pull the block off the ground. It just causes the block to keep sliding horizontally, just with a higher acceleration. So the vertical forces will still be balanced since the block is not coming off the ground. So we can still say, Newton's first law, the stuff in blue right here, that the upward force, or forces, Fn plus F sine theta, is still going to be equal to the downward force, the gravitational force, mg. So this rearrangement will still hold. Fn is equal to mg minus F sine theta. Well, let's take that and rewrite it. I'll just move that down here. Say Fn is equal to mg minus F sine of theta. Because what you can notice now is that if we increase the pulling force, if we increase this term right here, because that is subtracted, increasing this term will cause the Fn to go down, because the mg doesn't change. The mass of the crate and the Earth's gravitational field have not changed, so we increase the subtracted term, and that causes the normal force to go down. So for your justification for that, because it just says briefly justify your answer, it doesn't say to do it without calculations. You can do it either way. You can actually just take the calculation and show it, and then say something like, as F increases, just put an upward arrow, the Fn decreases, and mention something about because that second term is subtracted. Or if you want to do it as a more kind of physical answer without worrying so much as the math, you could just say that the increase in this pulling force causes there to be more of an upward force. So since the two upward forces have to balance out gravity, if there's more of one force, there has to be less of the other to balance out gravity. And part D, the increase in the man's pulling force causes an increase in the block's acceleration. So just give two distinct reasons why the acceleration increases. So if you look at what's going on horizontally, because that's where the block's accelerating, we only have two forces. The force going to the right, F cosine theta, and the force going to the left, the force of friction. So the first reason should be a pretty obvious one, that if you increase that pulling force, that means the horizontal component of that force is also going to increase. So if this force increases, that leads the forces to become even more unbalanced to the point where there's an increase in the acceleration. So you can just say that the horizontal component of the pulling force increases since the overall pulling force increases. The second reason is slightly less obvious, but a lot of times what happens on these AP questions is they'll give you a hint in the previous part of the problem when you have to write one of these kind of more drawn out explanations. And the hint actually came from the part you just did, because it asked you specifically about the normal force, and you just saw that the normal force decreases. And now if you look at what's over here, we have the frictional force, and you know that the equation for kinetic friction, FF, is equal to mu k Fn. So you can see that, according to this equation, if the normal force goes down, which it does, as we established in part C, if this goes down, since it's directly related to this, you can say that the frictional force would also go down. So that's the other reason the block increases, is because in addition to this force on the right side getting bigger, at the same time, this force on the left side gets a little bit smaller. And ultimately that leads to an even greater unbalancing of forces, causing the increase in acceleration.